Okay, good afternoon, everyone. So welcome to the Chemistry Olympiad training. Today we'll be doing speed of reaction. Now, the idea is not difficult. We know that some chemical reactions actually are very slow, whereas some other reactions are very, very fast. So what differentiates the fast reactions from the slow reactions? There must be a reason why certain reactions are much, much faster and certain reactions are much, much slower. But first, we need to understand this concept called speed of reaction. What do we mean by the speed of a chemical reaction? So take, for example, you may have heard of chemistry. Previously, before you even start learning chemistry, you will hear the word explosion. You think chemistry is about explosions. Explosions are, of course, very fast, right? They happen in the flash. Okay, in the flash, they are over. So explosive reactions are very fast. So why is it that starch is something that you can find in the supermarket? Why is it that starch, something that looks so safe, could actually cause a pretty bad explosion? All right. So actually, there was this event whereby there was colored starch powder thrown into the air. It was part of a party, but sadly, that triggered off an immediate explosion. So why is it that starch powder so readily explodes? All right. So hopefully, after this whole session, you will have some idea. But first, let's define what is speed of reaction. Well, it's not difficult, right? If a fast reaction means that the product is formed very quickly, that means the product concentration increases very fast. Or the reactant is used up very quickly. That means the reactant goes down very fast. So in short, a speed of a reaction is the rate of change of either the product or the reactant's concentration. How fast does the concentration of the product go up? How fast does the reactant go down? Okay. Now, this word rate of change is always linked to this word called gradient. The way you can tell from a graph whether the rate of change is fast or slow is to look at the gradient. So if we look at the gradient, if the gradient is steeper, it will have a higher speed of reaction. So take, for example, I give you two graphs, product, reactant concentration. Product increases with time because you are forming the product. You have more and more product with time. The thing is, if it's very steep, it's very fast. Reactants are used up, so they go down with time. So again, if it's steep, it's very fast. Okay? All right. Okay? So you can see in both graphs, the steep part occurs right at the beginning of the graph. You notice over time, the gradient becomes less and less steep until it comes a point where the graph becomes horizontal. So for the Sec 3s, you just did coordinate geometry, all right, in your E-math. When the graph becomes horizontal, the gradient is 0. And in this case, you just learned that gradient is related to speed of a reaction. So in this case, if the gradient is 0, it's the same as saying the speed of the reaction is 0. What does it mean for a reaction to have 0 speed? The reaction has 0 speed means the reaction has stopped. Why will a reaction stop? A reaction stops when the reactants, the raw materials, have been completely used up. Okay, so every single graph will proceed like this. It starts off the steepest, and then the gradient becomes less and less steep, telling you that the reaction is slowing down until a point where it plateaus, it's horizontal line. When it's horizontal, the gradient is 0. And that means the speed of reaction is 0. Okay, so that's how we graphically interpret how fast a reaction is. Now, how do we determine the product and reactant concentration? There are good ways to do that. One way is a titration. All right, so for my Sec 3s, you might have seen this word a lot in the notes. A titration is an experimental technique that allows you to determine the product or reactant concentration at every single point in time. Okay, but for now, we just need to be concerned with gradients, how steep or how gentle. Okay, moving on to the next concept. Why would some reactions be fast? And this is the collision theory of reactions. So this is called collision theory. Now, as the name suggests, the theory tells you it's about collision. Collision between what? Collision between particles. Remember, if you go back to the very, very starting point of chemistry, even in Sec 1, you learn that everything is made of particles. Particles are in constant random motion. So particles are constantly moving. But as the particles move, they collide with one another. Does every collision, though, result in a chemical reaction? Clearly not, right? If every single collision resulted in reaction, then everything should be equally fast. But that's not the case. Some reactions are super fast, some are super slow. So clearly, it's not just about collisions. The idea is the particles must collide in the right geometry. So if you think back to covalent bonding, all of you, when you first learn covalent bonding, you will have learned to draw molecules like H2, Cl2, CO2. But you also drew bigger molecules, right? Take, for example, okay, some of you, you're Sec 3s, right? You're in my class, you would have drawn certain molecules that are pretty big. For instance, you would have learned to draw things like SO3. You would have drawn BCl3. So bigger molecules. Now, bigger molecules have something important. The bigger molecules are not flat. Most of the bigger molecules have a three-dimensional shape, meaning they are not symmetrical. So the particles have to collide in the right angle, right geometry, or else the groups that actually want to react and bond will never meet each other. So the geometry is important because molecules are not flat. Next, not just geometry. You need to collide together with sufficient energy. If you don't have energy, you cannot overcome the forces of attraction within the molecules. You will need to overcome forces of attraction, or else there is no way to form new bonds with new things. The whole idea of a reaction is to bond with something new. To bond with something new, you must have energy to have broken your old bond. Okay? So that's the idea. So it's about geometry and energy. So not all collisions will fulfill the right geometry and right energy. Hence, a collision between reactant particles with the right geometry and sufficient energy is called effective collision. It's called effective collision because the collision effectively results in a reaction. And so we come to this conclusion. If a reaction is to be fast, that means there must be a high frequency of effective collisions between particles. All right? It is because the particles are colliding, and not just colliding. The collisions have a high frequency of effective collisions. Therefore, the reaction is fast. Okay? And remember, effective collisions must have the right geometry, sufficient energy. Both things. And these are a result of bonding. A chemical reaction involves forming new bonds while breaking old bonds. So I need the right geometry to form new bonds with, and then another thing, I also need sufficient energy to break the old bonds that I had. Okay? So now that we understand collision theory, we are better able to understand this concept called activation energy. And this is something that we need to know. Now, if we were to plot energy of a reaction, so we start off with the reactant. Reactants means what you started with. The reactants have a certain amount of energy. The products have a different amount of energy. Now, in this case, you can clearly see the energy went down. That means going from reactant to product, my energy went down. Where did this energy go? Where did it go? It can't just disappear, right? So the idea is the energy is lost to the surroundings, or you can say released to surroundings. And for all of us, we have learned this word before. A reaction that loses or releases energy is called exothermic. An exothermic reaction is where it releases energy go out to the surroundings. This means that the final product must have less energy left because some of the energy was released. Okay? So this is an exothermic reaction. Another way to say exothermic is a negative delta H value. Delta H is basically the energy change. The enthalpy or energy change of this reaction is negative. Why negative? Because final is lower than initial. It went down. If you go down, it's a negative, it's a loss. Okay? Now, besides that, we also need to know it doesn't just jump down from reactant to product. There is a pathway. And this is the pathway in yellow here. Your reactants need to meet, collide, form new bonds, break old bonds. That's the pathway, the drama for the reaction to happen. And this drama involves taking in energy, then releasing energy. Go up in energy, come down in energy. Right? So every reaction has a certain minimum amount of energy to start. Now just imagine if you are like a car going up or a roller coaster going up. You must have energy to go up to the top and then come down. If you don't have enough energy to even get to the top, you will never react. So this activation energy is the minimum amount of energy for effective collision to take place. It's the minimum amount of energy. If it doesn't have that amount of energy, it can't scale the top of the pathway. It can't go up and come down, right? Now, so how do we deduce the activation energy from this graph? Basically, you start from the starting point, which is reactants. You measure from the reactants to the top, the maximum point, how much energy. Now, this is quite crucial because in the chemistry Olympiad, they will ask you questions where they give you this graph and they will ask you, where is the activation energy? You need to know it's from the starting to the top. That's the activation energy. All right. So from this graph, I can tell the activation energy. I can also tell the reaction loses energy to the surroundings. It's exothermic. Okay. So that's for exothermic reactions. Now, how about endothermic reactions? The reverse. Some reactions actually take in energy from the surroundings, right? So for instance, okay, thermal decomposition. When you are trying to decompose, let's say calcium carbonate, you heat up the calcium carbonate and the overall reaction is actually endothermic, meaning it takes in energy from the surroundings. So for endothermic reactions, actually, the only difference really reactant, product. The first difference is that you notice the product is higher in energy. But that makes sense. Endo takes in energy. The product must have more energy as a result. It must be higher. Next step, how do you get the activation energy? To get activation energy, start from the starting point, the reactant, go to the top. All right. Now, so I'm going to zoom up so you can see both side by side. So exo, endothermic. Immediately, even without me telling you, you can compare the activation energy. How high is it? You can clearly see if endothermic reactions tend to have a larger activation energy. So endo reactions tend to have higher activation energy. Activation energy usually is abbreviated as EA, so activation energy. Okay, you can clearly see that the endothermic one has a higher activation energy. If it has a higher activation energy, the reaction is slower. This is because your reactant particles will need even more energy to have an effective collision to react. Which is why, if you look all around you, there are actually many, many reactions around you which are exothermic. Exo is very common, but endothermic, the reverse, is very rare. It's very rare because endothermic reactions tend to be a lot slower. So at room temperature, you just don't have so many. In fact, there is one common chemical reaction around you, which is endothermic. It takes in energy. Doesn't take in heat, it takes in light. The chemical reaction around you, which is endothermic, takes in energy from the sun, is called photosynthesis. So photosynthesis is probably the only common reaction which is endothermic and can take place at room temperature. But there are so many other exothermic reactions that can take place at room temperature. So you can really see the difference, all right? The difference is because endothermic reactions tend to be much slower, and that's because of the higher activation energy. Okay, so for the sec force, you would have learned this, but I wonder, did you make this connection? This connection is important, all right? Endothermic reactions are rare because they tend to have higher EA, activation energy. Okay, and finally, we come to reversible reactions. So the sec 3s, you have also learned reversible reactions. You have learned that weak acids dissociate partially and reversibly. The idea of a reversible reaction means it can go forward, it can go backwards again. So forward, backwards. Okay, so the only difference, of course, is where did you start? So of course, forward, you started with nitrogen and hydrogen. You ended off with ammonia. That's forward. The reverse, backward, is from ammonia going back to nitrogen and hydrogen. So you can see the activation energies for the forward and backward are different. Okay, so you can see the activation energies are not the same. Okay, so you must be able to label the activation energies because your Chem O is an MCQ exam. They will ask you, okay, where is the activation energy? All right, so you need to know which arrow represents the activation energies. All right, Ken? So the point is not to memorize anything here. The point is just, do we know how to interpret such graphs to get the activation energies and to differentiate whether it's exothermic or endothermic? Okay, so that's the point of page 4. Now we're going to move on to page 5, and you can see a lot of words. I'm not going to go through every single word. Hopefully, after some time, you will see a pattern, a central theme emerging from the next few pages. Okay, so for the sec force, I hope you already know the central theme of this chapter. Okay, so now page 5. Now, there are many factors affecting the speed of reactions. Honestly, if you were to read through these 5, out of these 5, you already knew at least 3 of them because you have encountered them even in secondary 1. So take, for example, in Sec 1, your science teacher brought you to the lab and you probably tried to dissolve sugar in water. Dissolving sugar in water is a physical change, but nonetheless, the speed of dissolving depends on temperature because you know from experience, sugar dissolves faster if you used hot water. Next, whether you use rock sugar or granular sugar, which is basically the powdered sugar, makes a difference. Rock sugar takes very long to dissolve, whereas granular sugar is much faster. Hence, you already know how temperature and surface area affects the speed of a reaction. Okay, now my job here is not to read off the lines. Okay, I'll just bring you through the main concepts, and thereafter, let's move to the A level and to quantify this mathematically. First, temperature. The higher the temperature, the faster the speed. That's obvious. But why? So, for those doing physics, you would have learned temperature is a measure of average kinetic energy of particles. It's kinetic energy. So when you have a higher temperature increase, the reactant particles have more kinetic energy. That means they move faster. If they move faster, obviously they will collide faster. Okay? Besides that, when you have more energy, what it also means is you will have more particles with sufficient energy. What is sufficient? Just now we said, right? Sufficient means it must be equal or more than the activation energy. So we say the number of reactant particles with energy greater than or equals to the activation energy increases. That makes sense. When you heat something up, temperature increase, they should have more energy. Therefore, more particles should have sufficient energy. Sufficient is equal to or more than the activation energy. So putting everything together, the particles got more energy, they move faster, got more particles with enough energy now. Therefore, the frequency of collisions increases, frequency of effective collisions increases, therefore the speed increases. We say this word just now, frequency of effective collisions. Frequency of effective collisions is the main factor behind the speed of reaction increasing. All right? So the frequency of effective collisions requires your particles to be the right geometry, right energy. What is the right energy again? More than or equals to activation energy. Okay? So this is Sec 4. This one is O level. Now let's go to A level. So now I have a graph here. This is called the Maxwell-Boltzmann energy distribution curve. Now, the molecules or particles in a sample do not have the same amount of energy. They can't. Okay, they can't. Okay, molecules don't necessarily all must have the same amount of energy. Okay, that's why we talk about average energy, because they have different amounts of energy. We take the average. Okay, you won't calculate the average. You will not. All right. It's just that this distribution you can obtain through experimentation, through mathematical modeling. All right. Now, if you notice this distribution, there are two temperatures, two different temperatures. T1 is a lower temperature, whereas T2 is a higher temperature. So the Maxwell-Boltzmann distribution curve basically shows you graphically what happens when temperature is increased. You notice a few things. The shape of the graph changes. As the temperature increases, the peak moves, the maximum moves to the right-hand side. You notice that, right? The peak moves to the right. It also moves down. And the curve broadens. The curve widens. Okay? Now, this is important because the area under the Maxwell-Boltzmann distribution curve, the area, provides a number of particles. So if we choose activation energy, then we look at the areas. The area under the curve from activation energy onwards will give you number of particles with energy from activation energy onwards. In short, the area under the curve from activation energy gives you the number of particles with sufficient energy. Remember this phrase, greater than or equals to activation energy means sufficient energy. So let's look. The area under the green color graph. The area under the green color graph is larger. The area under the curve is larger when temperature is increased. What that means is that you have more particles with energy greater than or equal to activation energy. Okay? Now, why do I introduce this here? Because for the Chem O, while they will stick to the O levels, they do not rule out getting you to interpret the graphs typically taught at A level. This is why you need to know the Maxwell-Boltzmann distribution curve. For the Sec 4s, you have learned this concept, area underneath a graph. Area underneath a graph is an integration. So actually, to obtain the number of particles, you could do that. If you have the equation for the Maxwell-Boltzmann distribution curve, you just need to integrate from the activation energy till infinity. All right, and that will allow you to calculate the number of reactant particles with energy greater than or equals to EA. And that's what typically we do when we study chemical physics. All right, we do a lot of integration here. So for my Sec 3s, integration is something that you learn in A Maths in Sec 4. Okay, so that's Maxwell-Boltzmann distribution curve. Okay, which tells you how temperature affects the speed of a reaction. Now next, we'll move on to concentration. Concentration is not difficult. The more concentrated the reactants are, the faster the speed. Why? When something is more concentrated, we basically have more particles in the same volume. So we say the number of reactant particles per unit volume increases. Concept is very simple. Let's say if you are in an MRT train, if you are in an MRT carriage that's empty, there's only two people, you won't collide into each other unless you deliberately wanted to, right? But now think, if the MRT carriage has like 200 people, everyone is literally sandwiched next to each other. If you are literally crammed into the same carriage with 200 people, the frequency of collisions between you and the person next to you must be higher, right? So that's the idea. An empty MRT carriage, very low concentration. A very packed MRT carriage, very high concentration. So the idea is the frequency of collisions must increase if the concentration increases. Therefore, frequency of effective collisions will also increase. Okay? Now, concentration is for something which is aqueous. If you recall, aqueous means dissolved in water. Typically, we would only use concentration for something which is aqueous. Okay? Which is why some of you have begun to ask me, oh, Mr. So, how come our acids and bases, you keep writing dilute, dilute, dilute? Yes, because if I use concentrated acid, the reaction is very, very fast. If the reaction is very, very fast, it could be very, very dangerous. That's why we do not use concentrated HCl in the lab, because concentrated HCl should have a very fast reaction. It's dangerous, right? Okay, moving on. Pressure. Now, pressure of a gas. Again, this is not difficult. How do you pressurize a gas? You have been taught this since primary school, because you know that gases can be compressed. So this word pressure links you to think about compress. Compression means what? I use a piston, I push down hard on the gas, right? So the same gas, when compressed, occupies a much smaller volume. Simple, right? Now, so if it's compressed, that means the pressure is higher. So higher pressure means compressed. Compressed means the particles are packed more closely together. Then we are suddenly back at the MRT carriage scenario just now. If it's an empty carriage, we do not collide so much. But if we are compressed into a very tight, small space, we are packed closely together, then our frequency of collisions increases, our frequency of effective collisions increases. Hopefully you see a pattern by now. Every single factor involves frequency of effective collisions. You must always come back to the concept of frequency of effective collisions when discussing speed of reaction. Okay, so far we have gone through temperature, concentration, pressure. Now pressure is only for gases because only gases can be compressed. Liquids can't, solids can't. Okay, now this is also the reason why generally, if a reaction involves a gas as a reactant, we will use a high pressure. Okay, so for the Sec 4 students, you might just have learned alkenes, right? So you would have learned hydration of alkenes. So for the Sec 4 students, to hydrate alkene, we use steam at 300 degrees Celsius, concentrated phosphoric acid catalyst. But more importantly, you need a high pressure of 65 atmospheres. If there's no high pressure, alkenes don't react with steam. All right, for the SEC4s. Okay, for the SEC3s, we will do this soon. We will do nitrogen react with hydrogen. They don't react together at atmospheric pressure. That means right now, around Earth, atmospheric pressure, they don't react. You need to use 250 atmospheres. That's 250 times our current pressure for N2 to react with H2. All right. Okay, then we go to surface area, which is about powdered versus large lumps. So just now I said about the sugar. If you use powdered sugar, of course, it will dissolve faster. For the bio students, you have already encountered this because in bio, you don't say surface area. In bio, Ms. Bo would have taught you the correct term is surface area to volume ratio. All right, so we don't actually say surface area. Okay, in chemistry, that's fine, but in biology, we will always say surface area to volume ratio, right? So for the biology students, you must recall, Ms. Bo would have told you things like, in our digestive system, all right, the small intestine contains numerous small projections called villi. The villi in turn have folds in the membranes called microvilli. The purpose of these villi and microvilli is to increase the surface area to volume ratio for the absorption of nutrients into the bloodstream, right? Another example, root hair cells. Root hair cells are specialized cells with a very long and narrow projection so that they have a higher surface area to volume ratio for the absorption of water by osmosis from the soil. Okay, so basically it's the same concept. The idea is how much surface area is exposed. And this is where perhaps it's a bit confusing. Powder has a larger surface area. A powder has a larger surface area exposed than a large lump. Now, how do we understand this? A large lump, only the surface, outer surface can react, What's inside cannot react, not exposed. Which is why a large lump, only the outer surface exposed reacts. Inside so much not exposed cannot react. That's why large lump very slow, because you need to take layer by layer by layer off until you reach the inside. Okay, so generally speaking, powders react much faster. Large lumps react much slower, right? And we come to the last concept of today, which is catalyst. And I want to spend some time on catalyst. So the Sec 4 students, okay, I'm not sure if Mr. Lee printed my enrichment. We are going to do the enrichment basically for speed of reaction. Now, catalysts are some things that the bio students would have heard of it because you have learned enzymes. Enzymes are biological catalysts. But catalysts in general are chemical substances which speed up the reaction and remain unchanged. But how do they speed up a reaction? Catalysts provide an alternative reaction pathway with lower activation energy. Catalysts literally provide a different route for the same reaction. It's almost like a new MRT route just opened that allows you to get to your destination much quicker. Okay? So instead of going through the words, let's look at the graph at the bottom. The activation energy with the catalyst is lower. It effectively lowers the barrier, the hump that reactants must cross. And today, for the next 15 minutes or 20 minutes, we're going to ask ourselves, how? How do catalysts lower the activation energy? How do they provide this alternative pathway? Okay, for the bio students, you might have heard of the lock and key hypothesis. That is a pathway, right? The pathway that enzymes help to do this is, the structure of the active site is complementary to the structure of the substrate. So substrate enzyme bind. That's a pathway. Okay, but are there other pathways in which catalysts could lower the activation energy? That's what we're going to explore for the next 15 to 20 minutes. All right, so on the next page, I've summarized the properties of catalysts All right, please read it yourself later, but can I just draw your attention to the first one? So we are on page 11. So on page 11, there are various characteristics of catalysts. The most important one is only a small amount of catalyst is needed. You don't need to add huge loads of catalysts. Next, a catalyst is selective, meaning you couldn't use the same catalyst for like 20,000 reactions. Typically, a catalyst will only speed up one or at most two types of reactions. So to speed up different reactions, I need to explore different catalysts. And this is why chemistry, you could build a whole PhD around a catalyst. Because if you found a catalyst which works for a particular reaction, that's a PhD already. Because different reactions just require different catalysts. Okay? Now, common catalysts include finely divided iron. So now we shall understand what is finely divided. Fine divided. Another word for this is powder. Finely divided just means powdered iron. Another one, platinum, rhodium, vanadium 5 oxide. Just look at these metals. Iron, platinum, rhodium, vanadium. All these metals which are catalysts, they all belong to transition metals and their compounds. Transition metals and their compounds are able to speed up chemical reactions, which is why transition metal chemistry is super important, because that's where the money is. If you are able to speed up a reaction, of course, your reaction becomes more efficient. You produce more in the same amount of time. If you produce more, you sell more profits. Okay, so of course, these are very common catalysts. Right now, if you pursue a PhD in chem, your job is to find a new catalyst which is even more efficient, perhaps environmentally more friendly as well. Okay, but just take note, transition metals and their compounds are the common catalysts. Okay, so now we shall move on to catalysts for the next 15 minutes. So first we're going to talk about enzyme. Enzyme is on page 12. Now, enzymes are biological catalysts, meaning they speed up chemical reactions within living things, living organisms. So first things first, enzymes are proteins. Mostly, not all actually, but most enzymes are proteins. Enzymes are very specific. We mentioned this just now. One enzyme, one type of reaction. The enzyme that can speed up digestion of carbohydrate will not speed up digestion of fats. Different reaction, different enzyme. All right. So enzymes are specific because they only bind to a specific substrate. Because the structure must be complementary. The active site, which is where the enzyme binds, must be complementary. So what is active site? Active site. Active site is the place where the substrate binds. All right. So what is substrate? Substrate is a very fanciful way of saying what binds to the active site, the molecule which binds to the active site. Okay, so in this case, A and B, they are substrates, right? So A and B bond or bind to the surface of the active site. Now, once they bind, this thing is called an enzyme substrate complex. So remember just now we said, catalysts provide alternative reaction pathway with lower activation energy. The enzyme substrate complex is the pathway that lowers the activation energy. Because the enzyme substrate complex is a fantastic place that brings together A and B for the reaction to happen. So the enzyme substrate complex is one way of ensuring, that the reactants are in the right geometry to collide, right? Because the active site is engineered naturally such that the substrates are in the right geometry. They are facing each other in close proximity to collide, right geometry. Perfect for an effective collision. Okay, so now I hope the bio students are really linking the lock and key hypothesis, enzyme substrate complex, to effective collision. The enzyme substrate complex is not just a word. It brings together A and B in the right geometry for an effective collision to take place. Okay, so with that, you can clearly see why enzymes are specific, because they cannot just bind to any random molecule. The structure is specific. Okay, and because the structure is so important, enzymes are sensitive to temperature and pH. Because temperature and pH, if it's too extremely high or extremely low, it will cause the active site of the enzyme to lose the structure. When the active site loses the structure, it's called denatured. Okay? The structure is so important. If the structure is lost, it can no longer bind to the substrates, and that's it. No more speeding up reaction. Okay? Now, we are doing this now because this is also in the O-level syllabus. All right? So it's quite likely that you will need to know something about enzymes, whether you are taking biology or not. Okay? Now, the next few pages, page 13 to page 16, 17, will be self-reading. You will read through how do we measure the speed of reaction in the lab. So please read through page 13 to page 17 yourselves. Now we shall immediately go to page 18 and 19, where we will hopefully finish off. Okay, let's go to page 18 and 19 of the notes. Okay, so now we have broadly covered what we need to cover today. Okay, as I mentioned, we will spend some time looking at how do catalysts provide alternative reaction pathway with lower activation energy, right? So we went through enzymes. Enzyme substrate complex is a way of providing an alternative reaction pathway. Okay, now, but in chemistry, we like to categorize things. So like enzymes, we want to categorize it somewhere, right? We need to give it a group, a name. So catalysts can be broadly divided into two types depending on their state of matter. In case you forgot, state of matter is solid, liquid, gas. But in chemistry, there's one last state of matter that we often forget. Aqueous. Okay, it's quite common now to find aqueous state in chemistry because many of our reactions take place in the aqueous solution. Okay, so we divide the catalyst into two types depending on their state of matter. The first type is heterogeneous. Hetero, this word means different. So in this case, heterogeneous means the catalyst is in a different state from the reactants. Maybe the reactants are gases, but the catalyst is a solid. Okay? Homogeneous, homo means same. That's why for the bio students, again, a simple word they all learn, homeostasis. Homeostasis means I'm trying to maintain the body's internal conditions in the same condition, same level. Homeostasis. So homo means same. In this case, homogeneous means same state. The catalyst is in the same state. Typically, homogeneous will be aqueous. Both the catalyst and the reactants are aqueous. Okay? But not always, not always. Okay, I'm saying typically. Maybe I should write the word typically there. Because this is chemistry, okay? Typically, chemistry, we do aqueous. So now we're going to look at how homogeneous and heterogeneous work. They work by different methods. Remember, both of them still provide alternative reaction pathway. It's just that the methods they provide the pathway is different. So we are going to start with heterogeneous. Heterogeneous catalysts. Okay? Remember hetero, oh my God, spelling error. There's heterogeneous. Heterogeneous means different state. The catalyst is in a different state from the reactants. Now, heterogeneous catalysts work by providing a surface. It's just a surface for the particles to come together. This is crucial. When the particles come closer together, they will be in the right geometry. If you allow the particles to just collide randomly, they may not be in the right geometry when they collide. But by putting them together, they will be in the right geometry. So a very good example, which this is from the TYS, is about palladium. Palladium is a transition metal. You can find it in the middle of the periodic table. The symbol for palladium is Pd. We're talking about palladium metal itself, not the compound. So Pb is a very, very expensive metal used in catalytic converters. So basically what catalytic converters do is that they oxidize carbon monoxide to carbon dioxide. That's one of the reactions. So in this case, we have O2, that's oxygen. We have CO, carbon monoxide. If you just allow the CO and the O2 to randomly float around, they will collide, but they may not be in the right geometry. They may not have sufficient energy. Maybe the CO collide with CO, no reaction. There's only reaction if CO collide with O2, right? CO plus CO got no reaction. CO plus O2 got reaction. So the idea is, okay, so the palladium can help. The palladium provides a surface for the atoms to bind. So what happens is the first stage is adsorption of O2. Please highlight the adsorption, not ad. Adsorption means, in layman words, to stick. In a more difficult word, adhere. So the oxygen molecule adheres to the surface of palladium. Now, the effect of this, of course, is that when the oxygen molecules adhere or bind to the surface of palladium, it will weaken the covalent bonds within oxygen. Oxygen, O2, has a double bond between O and O. Why double bond? Oxygen is group 16, 6 valence electrons, it needs 2 more. If you need 2 more electrons, oxygen must share 2 electrons with another oxygen. O2, double bond. Okay, so when O2 binds to the palladium, the double bond weakens and breaks. Well, that's good, right? If it breaks, then the next step, CO, carbon monoxide, binds to palladium. Then the reaction happens on the surface of palladium. What reaction? The reaction between oxygen and carbon monoxide happens. Okay? Now, there was a question that was just asked, how does adsorption affect the oxygen's covalent bonds? Oxygen only needs 2 electrons more. In fact, it couldn't accept more than 2 electrons, right? So by sharing electrons, 2 electrons with the other oxygen, I have achieved a fully filled outermost shell. But now, if I still want the oxygen to bind to palladium, that means I'm forming a bond with palladium, right? How will oxygen form a bond to palladium when it already has a fully filled outermost shell? Well, one way is to break the original bond. Let's break the original covalent bond and form new bonds to palladium. And that's what happens. All right. The binding of the oxygen to palladium forms a bond with palladium, but breaks the original double bond in oxygen. Okay. Now, the beauty is the reaction on the surface. When it reacts on the surface, it reacts faster. Why is it faster? Because the oxygen and carbon monoxide are closer together. They are made to be closer together by the palladium, which is acting as sort of the matchmaker, the surface that matchmakes oxygen and carbon monoxide. Okay? Of course, when the reaction has happened, it forms CO2. The product is CO2, right? The product will dissolve. Dissolve means go away. And importantly, after the CO2 goes away, the palladium remains chemically unchanged. This is crucial. Because it's chemically unchanged, only a small amount of palladium is needed Because the palladium surface is chemically unchanged, it is able to be reused. It could catalyze and speed up another set of oxygen and carbon monoxide. The same catalyst could be used again and again and again and again. That's why only a small amount of a catalyst is needed. Now, this is heterogeneous because the palladium is solid, whereas oxygen, carbon monoxide are gases. They are in different states. Now, after describing to you how palladium works, actually, this sounds familiar to enzymes, right? What we said about enzymes just now. Oh, enzymes, they bind the substrate binds to the enzyme to form enzyme substrate complex. Isn't that what palladium is doing? Palladium is trying to bind oxygen and carbon monoxide. Once they bind, reaction happens on the surface. It's the same concept as an enzyme substrate complex. That's why enzymes can be considered heterogeneous catalysts. Okay? So for those doing bio, heterogeneous catalysts, how this works is very, very similar to how the lock and key hypothesis works for enzymes. Okay? So that was heterogeneous, where the catalyst is in a different state from the reactants. Now we move to page 21, which is homogeneous. Homogeneous means same state. And the best way to learn this is to look at the examples. Okay, so I mentioned that usually it's aqueous, but how about gaseous state? Now, gaseous state can also have homogeneous catalysts. So we are going to look at example 1. In example 1, we talk about chlorofluorocarbon, CFCs. Chlorine. Chloro is chlorine. Fluoro, fluorine. So CFCs have chlorine, fluorine, carbon. So CFCs actually help to speed up the breakdown of the ozone layer, which is not great. It's not great, because the ozone layer is necessary to protect us from ultraviolet light from the sun. Okay, ultraviolet light can be quite dangerous, especially for skin cancer. Okay, so how do CFCs speed up the breakdown? CFCs produce chlorine atoms when they are exposed to ultraviolet light. Chlorine atom is not Cl2. Cl2 is chlorine molecule. Chlorine atom is particularly bad because if you recall from your first lesson for atomic structure, the chlorine atom is 287. It does not have a fully filled outermost shell. If it doesn't have a fully filled outermost shell, it's very reactive. Very reactive because it wants to do all it can to get another electron in order to achieve a fully filled outermost shell. So the Cl atom is super reactive. It will react with ozone. So now let's look at the two equations. Step 1, step 2. Step 1, the chlorine atom reacts with ozone to form ClO and O2. Okay, it's just an equation. Step 2, the ClO from step 1 reacts with ozone again to form Cl and 2O2. So, how do the two equations, show that chlorine acts as a catalyst? You can tell chlorine acts as a catalyst once you highlight chlorine. Look at where chlorine is in step 1. Chlorine in step 1 is on the left side. Cl is used up. This one you learned before, right? If it's on the left side of the arrow, it's used up. Then in step 2, Cl is produced. So obviously you know used up and produced are opposite words. So what you are trying to say is in the first step, chlorine atoms are used up. In the second step, chlorine atoms are produced again. Produced again is called regenerate. So basically the idea is the chlorine atoms are regenerated in the second step, which means that the amount of chlorine would not change, right? You used up one, you formed another one. The net effect is you didn't change the amount of chlorine atoms. So this fits our criteria. The catalyst remains chemically unchanged at the end of a reaction. You can tell that because Cl is used up in step 1 and Cl is regenerated in step 2. That's why only a small amount is needed, right? Because if it's regenerated, you don't need so many, you know. A small amount can actually speed up the destruction of ozone, you know, many ozone. Yeah, which is why chlorofluorocarbons are dangerous. All right. Now, so now we shall write the overall equation. Okay. And I think we will end off with this. Now, to write the overall equation means I want to combine step 1 and 2 into one equation. And the way to do that is to find out the common term. The common term is what is produced in step 1 and used up in step 2. Do you realize ClO, which I've highlighted in blue, is produced in step 1, used up in step 2? So once you have realized that, you realize that, hey, this is like the intermediate. It's not a product. It's not a product because you formed it and you are going to use it next. It's an intermediate. And because it's an intermediate, what we need to do is that we just need to make sure, oh, I formed one ClO. I used up one ClO. The number of ClO formed equals to the number of ClO used. Why must be the same number? Because you remember, chemistry is not magic. In Sec 2, you learn your molecules, your atoms can't just vanish. If you formed one ClO, you must use up one ClO as well to balance and ensure the number of chlorine and oxygen remains the same in the system. If the numbers were to be different, that means it's magic. You suddenly have more chlorine and more oxygen, or less chlorine and less oxygen. The idea is always the same number. So the way to combine the overall equation is always to locate the intermediate. The intermediate is what's produced in the first step, used up in the second step. Once you have found the intermediate, make sure the coefficients are the same. In this case, they are the same. If it's used up and then produced, it will cancel out, right? So what happens is the ClO will cancel out. What other thing will cancel out? What else is used up and produced? The Cl is used up and produced, right? So all the common terms should cancel out. Okay? All the common terms should cancel out because what is used up and then produced again cancels out because they are on opposite sides of the arrow. Do you realize the Cl is on opposite sides of the arrow? If they are opposite side of the arrow, they will cancel out. Same with the ClO, opposite side of the arrow, cancel out. You do this every day in algebra. You so happily cancel out the 2, right? Make sense? You cancel out the 2 because the 2 appears on both sides of the equal sign. So in chemistry, chemical equations, we don't use equal sign, we use arrows, right? Cl appears on the left, Cl appears again on the right. We cancel those out. ClO appears on the right, then appears on the left, cancel out. So once you have cancelled out, what are you left with? You are literally left with O3 and O2. On the left-hand side, I got 2 O3. One here, one here. 1 O3, 1 O3, 2 O3. And that's it. That's it on the left. On the right-hand side, what do I have? 1 O2, 2 O2. So in total, 1 plus 2, 3. All right, so the overall equation is just 2O3. O3 is ozone. 2 molecules of ozone became 3 molecules of oxygen. All right. Now, so going back to catalyst before we end, just give me 1 minute. So how does the chlorine atom act as a catalyst? How is this an alternative pathway? Now, it's an alternative pathway because chlorine reacted with ozone. It reacted with ozone to form some intermediate. This some intermediate is called ClO. That means it's an alternative pathway. It reacted with ozone to enable the formation of this intermediate. And this intermediate can go on to react with ozone as well. So the alternative pathway for a homogeneous catalyst is basically to take part in the reaction to form intermediates. This is different from heterogeneous. Heterogeneous is to provide a surface for binding. Just a surface. It's just a matchmaker. This one is not. This one is not a matchmaker. This one is an active member of the reaction. It takes part in the reaction to form intermediates and then is regenerated again at the end. So I react first to form something, but at the end, I'm going to come back again. I'm going to be regenerated again. So I'm used up first, then at the end, I'll be regenerated again. Okay, so it's very important. Homogeneous and heterogeneous, they do not work the same way. Now, you will need to know this. This is a concept typically taught at A level. But right now, even with this, you can actually see some of these concepts coming out. Okay, so yes, catalysts provide an alternative reaction pathway with lower activation energy. There are two ways to do that. It's either you just provide a surface for binding, or you become an active member and take part in the reaction, form an intermediate, but at the end of the day, you are regenerated. Okay, so two different ways of achieving the same outcome. Now, this was example 1 for homogeneous catalysis. I strongly advise you guys to actually read through example 2 and example 3 and have a think, and example 4 as well, and have a think about it. Now, for the Sec 4 students, I hope you will turn to the last page. So for the Sec 4 students, you just did integration in your A math. So I hope you'll look at the last page and see how does all your A maths come together. Okay, your A math comes together in the last page. So typically when I teach my pure science at Sec 4, I will do enrichment for this chapter. And this enrichment makes sense because they would have learned the relevant A math content in their lessons. So for the Sec 4 students in Fall Flourish, Mr. Tan probably just taught you rate of change, and he probably taught you how to integrate. So do you consider speed of reaction is a rate of change, right? If it's a rate of change, it's actually dA dt, where A is a reactant. Yes. And because it's a decrease, it must be a negative dA dt because it's decreased, right? Yeah. And so now, if I were to integrate it back, I can actually get the shape of the curve. And for the Sec 4 students, the shape of this curve is exponential, right? It's e to the power minus x. Okay? So yes, for my Sec 3s, this is how all the mathematics you learn comes together. You will use every single bit of mathematics that you have. Okay, this is not A level. This is actually university second year. So I used to teach this to my university undergraduates when I was their tutor. I'll teach them how to integrate like this to get back this function. All right, it's not difficult. You could do it with O-level A math. Okay. So for Sec 4s, can I please encourage you to read this? It's quite interesting to me, at least. Okay, so that brings us to the end of today's lesson. Okay, let me just pause the recording first and I will get questions. Thank you.